So now that we've had a short look at the early part of your vectors work from National 5, I'm going to continue to look at the remainder of the work on National 5 vectors that you should be familiar with. This bit here on the distance in 3 dimensions, you are familiar in your higher course with the distance formula, and really this is just an extension of the distance formula and being able to use it within a vector quantity. Basically your components or your coordinates, you can see down here in this pink section, if you've got points x1, y1, z1, x2, y2, z2, then the distance between those points in a three-dimensional diagram is given by, it's like doing Pythagoras in 3 dimensions. So you're basically subtracting your x's, squaring, and do the same thing with your y's and your z's, squaring, and then adding them, and then taking overall the square root. So that if you're asked to work out the distance between 2 points, you can do it using the distance formula. If you're given a single vector that represents the journey from one point to the other, then it's the same sort of idea. It's just basically Pythagoras. You square each of the components of your vector. So this is like working out your magnitude. So distance between points A and B, if you know the vector that represents A to B, then you can use the components and do the magnitude. However, if you hadn't worked out what A to B was, you could just use the coordinates in the distance formula method. So there's no real advantage one over the other. So here's an example of using the distance formula. So this is on your page, page 131. You might want to pause the video and fill this in. So to work out the distance between these two sets of points, of course you can label your points as you've got them there. So that would be your x1, your first point y1, z1, and then your second point, of course, is your x2, y2, and your z2. And you're just substituting into this distance formula in turn. So when you substitute in for your x's, you end up with 0 minus minus 1. So this bit here, that does eventually become positive 1 squared. And you've got 5 minus 4 squared. And you've got minus 7. And you're subtracting 1 squared. That gives you negative 8. Remember to make sure you bracket round negative numbers when you're squaring them. And that would mean that you'd end up with root 66, square root of 66, and that would be your units. And that doesn't simplify any further in terms of being a third. So that's just an extension of previous knowledge in terms of being asked to work out a distance. So other things that you should be familiar with, vectors which have got the same size and direction are said to be equal vectors. So if you're told that two vectors are equal, it means that each of their components, their x components, will match. So here A would be equal to D, your y components will match, and your z components would need to match if they were exactly equal to each other. Something that you again met in National 5 was how we add and how we can actually subtract vectors from each other. So we can do this on a diagram. So we can construct a little journey that basically says if you start out and you add on, so you take out the journey for the vector A, and then here you add on the vector B, and then you finish at this point, then it's like the shortcut route from start to finish is described as being the vector that represents A plus B. and that's what's called a resultant vector. And again, you mate that term at National 5 if you were ever asked to find the resultant vector. It's what you get when you add these two vectors together. So at National 5 you do a lot of work on a grid. You'd be sketching this out at higher. You're more likely to work with this in component form when we do that, when we are working with A, B's and C's. So again, if you've got three vectors, you can add them all and you can create this diagram. So that would be your starting point, this would be the finishing point, and your A plus B plus C, like the shortcut if you like, would be the resultant vector. So when you're adding vectors, you're adding what's called in nose to tails, how it's usually described, but it has to follow, and the arrows need to follow around that diagram. So when we do A plus B plus C, we end up, so that was our starting point, this is where we're finished, and the three vectors on three sides, the arrows are all going in the one direction following on, and your resultant vector takes you from starting point to finishing point. What happens when we're subtracting vectors is you want to be thinking about your rules that you work. When you're working with negative numbers, A minus B is exactly the same thing as doing A add negative B. And of course negative B simply means it's the same length as B, but the arrow would be going in the opposite direction. They've got exactly the same magnitude. So therefore, if you're trying to do or create a diagram to represent A minus B, you would basically be, there's your starting point, and when you get to the end of vector A, you would then be adding on the negative, so which would take you down to here, and that would be your finishing point. And then this vector here, the resultant vector, would be A minus B. So just remember it as being A add on, negative B is effectively what you're doing. Using components, and this is what's more common at higher, is to calculate adding together two vectors. So basically you're going to add your x's together, add the y components together. So for these two vectors here, your u plus v, you'd have 1 add negative 1 would give you your 0, 5 add 2 gives you 7, and 2 add the 0 at the bottom gives you the 2. When you're subtracting, you could, if you preferred, write it out as u add negative v, but there's no advantage over that because you are just subtracting them, and numerically it makes more sense it's easier to just deal with it as 1 minus 1. So that's 1 add 1, which gives you 2, 5 minus 2 gives you 3, and 2 minus 0 gives you 2. If you were drawing a diagram, it's better to think about it as u add negative v, but for a component form, it's okay to think in terms of subtraction. So this is just the second example that you're subtracting as well, just slightly harder because you've got fractions involved, so be aware a lot of this can be non-calculator. So here we've got 4 minus 1 for the x component, which is clearly 4 add 1 giving you 5. You've then got 3 over 2 minus the whole number of 3. So you want to be thinking about that as 3 over 2 minus 6 over 2 for your whole number of 3, and that is clearly going to give you minus 3 over 2. And likewise, when you're doing 3 minus 6 over 5, that would become 3 plus 6 over 5, and again you could write the whole number of 3 as 15 over 5 plus 6 over 5, and that's where the 21 over 5 comes from. So it is just about using your fractions. So this one here, if you're doing q add p, make sure that you take the terms in the order. Be careful that you don't misinterpret values when you do this. So adding together those two terms. You've got Q, add P, your answer here. You'd have minus 1 plus 4 is going to give you 3. You've got 3, add 3 over 2, that's like 3 plus 1.5, which is 4.5. I'm going to write that as a single fraction, 9 over 2. And then I've got negative 6 over 5, so that's like negative 1.5, plus the whole number 3, which is going to give me 9/5. And again, you can think that through in terms of fractions. So that's adding and subtracting with components. Something else that you did meet again is multiplying by scalar numbers. So if you've got a vector u, you can create a new vector that's 3 times the length of that by multiplying all the component values by 3. And likewise, you can multiply by negative scalar versions. You can also multiply by fraction. So if you were given u with components a, b, c, and you have to multiply, it multiplies each of the components inside the vector form. So in this example here, right, just being able to write down, find 3 times v. So we would write that down first of all like this, so with the 3 outside the bracket, and then knowing that that means that you get 3 times 1 would be 3, you get 3 times 5 is 15, and 3 times negative 3 would be negative 9. So with question 2 on that same page, you have to find negative 4r. So again, putting the negative 4 in front, you get negative 6, 3 and 1. So what's your negative signs here? 2 negatives multiplied together to give you positive 24. Negative 4 times 3 is negative 12, and negative 4 times 1 is negative 4. So shouldn't really be any issues with that. That should all be quite straightforward, I would have thought. It's just about jogging your memory because you have seen all this stuff before. The negative of a vector is simply the vector multiplied by minus 1. So all that happens is everything just switches round, the direction switches round, and you just change the components by negative 1. That's all that's saying. Now this is a very important bit, this next bit. This is some called position vectors, and this is where if you've got a point plotted in a coordinate plane. Now when you write down coordinates, they're written across the way. So the point P on this diagram here has got coordinates x along y in the way and then z up the way. So this is your x, this is y, and this is z. So that's the coordinates of the point. The position vector relative to the origin, so to go from O to P, and remember a vector, you're just describing the journey, how you get from the point O to the point P. The coordinates are simply written up and down the way to create your vector x, y and z. And that's referred to as the position vector, and we usually use the lowercase letter of the matching capital letter for it. Now, a very important result that you can get from this is if you're going between 2 points on a coordinate grid. So this diagram here demonstrates what the result is and how we get it. If you have the point A and the point B, and we said that relative to the origin, their position vectors were lowercase letter a, lowercase letter b, but we want to create a new vector that takes us from point A to point B. We can write this down in a vector journey. So to go from point A to point B, I can go from A to O because I already know what O to A is, but that means I also know what A to O is. That's just going in the opposite direction, so that's why I can write to do A to B. To do the journey A to B, I am going from A to O, and then I am following that by going from O to B, and that will take me straight from point A to point B. So this is like your vector addition. And of course we know that A to O is actually going against the position vector of A in terms of its direction, so that's negative A, but then going from O to B, that is in the usual direction for the position vector of B. And as you know, if you write a negative plus something, we can switch those two terms round and that's still positive, and then that would become negative. So we could write B add negative A, or we can write B minus A. And it's this result that is a kind of standard result for position vectors. For any 2 points that you're trying to find a vector or work with components, the quick way to get the single vector that represents A to B is it's always the second letter position vector that goes first, and then you've got a minus and then the position vector of the first letter. So if it's A to B, then it's going to be B minus A. If it's B to A, then it would be A minus B. And you can see that it also mentions this in your notes. If you've got P to Q, it's the second vector first, so it's Q minus P. And these represent the position vectors relative to the point. So to see this in practice, you've got this question on your notes page, and we would be writing down for this that you've been given these 2 points and you are asked to work out what is the position vector for, what's the vector representing to go from R to S. So what I would be writing down here is lowercase letter s underlined minus lowercase letter r underneath. That's the standard result. And your s, you turn it into a vector. So your point S, 4, 6, minus 1, is written that way. Your point R is 2, minus 2, 3, written this way. And then it's just a case of subtract those. So you get 4 minus 2 is 2, 6 minus 2, that becomes 8, minus 1, subtract 3, and that becomes minus 4. And that's essentially all the work that you have made at National 5. So you are going to practice using the position vector result that you've just seen there in exercise 13G in your textbook.